Okay, last Tuesday we studied what is throttling valve, and the energy balance equation for this throttling valve is the enthalpy H remains constant before and after this throttling valve. By the way, this throttling valve drops pressure. That's what it does. Okay, so if we want to increase the pressure of a fluid, we use compressor. And then if we want to decrease a pressure, then we use this throttling valve. So the energy balance equation is going to be the enthalpy H remains constant. Based on that, let's solve this problem together to learn how to analyze a throttling valve. Okay, so in this case, we have this throttling valve. Let's talk about the physics here. And there's an inlet here, number one. There's an exit here, number two. Saturated liquid vapor mixture enters this valve. That means we have a phase change process. Number three, saturated mixture. When you have saturated mixture, we need another property, that is quality X. By the way, the quality X is not given. The pressure P1 is 2000 kilopascal. So at the inlet, we don't have enough information to understand the system, because we only know pressure and we know it is saturated mixture, but we do not know the quality X. What about at the exit? We know pressure P2 is 100 kilopascal, and we know temperature T2 is 120 degrees Celsius. So based on what we learned from the energy balance equation, the enthalpy H remains constant. So that means we know pressure and temperature at the exit. Then you can determine the specific enthalpy H from this pressure and temperature. Since we know H2, H1 can be, we can know H1. If we know P1 and H1, then you can determine X. So that is the plan. So let's find H2 first. We have a pressure and temperature. How can we find this H? We need to determine the phase change process. How can we determine the phase change process? We can make a property diagram. So at this pressure, 100 kilopascal, we can make temperature diagram. We can make TV, TU, or TH diagram. Anything is fine. So let's make TH diagram. TH diagram looks like this. To complete this TH diagram, we need to know three properties. They are T set, HF, and HG. Where can we find T set, HF, and HG? From this pressure, 100 kilopascal. So where is 100 kilopascal? On this pressure table, table A3, pressure table, there is 100 kilopascal. T set is 99.63, and HF is this one, 417.46. HG is this one, 2675.5. So that's how you complete this TH diagram. On this TH diagram, we have number one, compressed liquid here. Number two, saturated liquid here. Number three, saturated mixture. Number four, saturated vapor. And number five, superheat vapor. So now let's find the phase change process. How can we do that? We made this TH diagram by using this pressure. So this one. Now we are going to find our system using the other property that we know, 120 degrees Celsius. This is temperature of the system. Where is temperature? This vertical axis. So let's find 120. 120 is greater than 99. So 120 should be up here. So what is the phase change process? Number 5, superheat vapor. So number 5, superheat vapor. This one. So now, if you know superheat vapor, how can you determine its specific enthalpy? You can go to superheat vapor table. Table A4, superheat vapor. Pressure is 100 kilopascal, which is 0.1 megapascal. So you can use any of the numbers in this table. And what is the temperature? 120. 120 is here. 120. So what is the property that we are looking for? These three. From VUH, we need H. So the property that we are looking for is 2716.6. 2716.6 kilojoule per kilogram. That is the specific enthalpy. Now, according to this energy balance equation, we know H1 is also 2716.6. So now we have 2000 kilopascal and 2716.6 kilojoule per kilogram. So this is H1, this is P1. Now, can you determine quality X? Yes, we can. By the way, we know this is a saturated mixture. If you have saturated mixture, we can use linear interpolation. For H, it's going to be H is HF plus quality X times HG minus HF. Then do we know H? Yes, 2716.6. Do we know HF? We can find it from where? From pressure table, 2000. So here is 2000 kilopascal. Where is HF? This number. Where is HG? This number. So let me use these two values. Let me write these two values on this equation. 908.79. This one is 2799.5. This one is 908.79. We have everything. Can you determine quality X? Now, yes, you can. If you do, you get 0.596. That's how you solve this problem. Any question? It's not that hard, right? The energy balance equation is simple. The rest of them is just finding a property using the table, right? Okay, we have two more thermodynamic devices to go. The next one is a mixing chamber. What is a mixing chamber? It's a device that has more than one inlet and only one exit. So we have two inlets and one exit. What happens is that there's a mixing between two fluids. So each of them may be at different pressure and different temperature. So whose specific enthalpy H is going to be different. So by solving this mixing chamber, we can learn how to determine mixture enthalpy. So let's do that. So when we have this mixture, we can come up with two equations as always. What kind of two equations? The same two equations based on conservation principles. Conservation of mass and conservation of energy. So let's talk about conservation of mass first. So mixing chamber has two inlets. Inlet number 1, inlet number 2, and it has only one exit, number 3. So the mass flow rates are m dot number 1 is the mass flow rate at the inlet number 1. M dot number 2 is the mass flow rate at the inlet number 2. M dot 3 is the mass flow rate at the exit. So I guess it's time to write the mass balance equation. The general mass balance equation is simple. Mass transfer into a system should be the same as mass transfer out of the control volume. So what kind of mass transfer that goes into this control volume? 1, 2. 1 and 2. So this one is m dot number 1 plus m dot number 2. This is the sum of the mass flow rates that go into this mixing chamber. And how many exits? Just 1. M dot number 3. So this is the mass balance equation. Very easy, right? Now let's talk about energy balance. How do you determine the energy balance equation for this particular control volume? It's simple. You start with the general energy balance equation. What is the general energy balance equation? Q dot in plus W dot in plus M dot at its inlet. This M dot has three forms of energy. First, specific enthalpy H, and second, specific kinetic energy, velocity square over 2, and third, specific potential energy. What about energy transfer out of this control volume? 3, heat, work, and mass. Heat, Q dot out, plus work, W dot out, actually power, plus mass leaving this control volume, M dot out. This has what? Three forms of energy. H, kinetic energy, and potential energy. So this is the general energy balance equation for steady state open system. So when we have a steady state open system, this is the general energy balance equation. And let's see. We usually do not heat a mixing chamber because there's no way, there's no reason to do that. And mixing chambers do not accept any energy transfer by work, does not produce any energy transfer by work. We usually neglect the change in kinetic energy or potential energy. So what do we have? The rate of enthalpy at the inlet, the rate of enthalpy at the exit, and a possible heat loss. So this is case by case. Sometimes you have a good insulation and you can neglect heat loss. If not, you need to consider heat loss. So in this problem, we have two inlets, 1 and 2. So this rate of enthalpy is going to be 1 and 2. M dot number 1 times H1, now 2. M dot number 2 times H2 is going to be Q dot out. This, by the way, this rate of heat loss case by case, plus exit number 3, m dot 3 H3. So this is the energy balance equation for this mixing chamber. That's it. That's all the theories that you need to solve any thermodynamics problem related to a mixing chamber. Then let's solve a problem together. Which one? This one. A hot water stream at 80 degrees Celsius enters at number 1 and 20 degrees Celsius water entering at number 2. So there's a mixing. So at the exit, the water temperature is going to be 42 degrees Celsius. We want to know what is the mass flow rate of the inlet number 2 to make sure the exit temperature is 42 degrees Celsius. Okay. Assume all the streams are at a constant pressure of 250 kilopascal. So at the inlet number 1, we have 250 kilopascal, 80 degrees Celsius. At the inlet number 2, 250 kilopascal and 20 degrees Celsius. At the exit, 250 kilopascal and 42 degrees Celsius. What is the first thing we need to do? To determine H, we need to know the phase change process. So let's do that. How do we determine the phase change process? By using a property diagram. So let's look at the inlet number 1. We have 80 degrees Celsius, 250 kilopascal. So I'm going to use this pressure. At 250 kilopascal, we can make TH diagram. This one looks like this. To complete this TH diagram, how many properties do we need? 3. What are they? T set, HF, HG. So where can we find this T set, HF, HG? From table A3. So there's a table A3, pressure table. So let's find 250 kilopascal. T set is 127.4. So T set is 127.4 degrees Celsius. Wait a minute. The inlet is 80 and another inlet is 20. The exit is 42. So let's find these 3 temperatures. Inlet is 80, still less than T set. Another inlet is 20, still less than T set. 42, still less than T set. So all 3 inlets and exit is at number 1, compressed liquids. They are all compressed liquids. Then how can you evaluate a property of compressed liquid? If it is compressed liquid, phase change process number 1, there are 2 different ways to determine its property. The first one is when pressure is high. How high? Equal to or greater than 2.5 megapascal. In our case, only 250 kilopascal. When pressure is low, or less than 2.5 megapascal, in this way, we go to a table, A5. In this way, we assume that the properties of these compressed liquids can be approximated as the properties of saturated liquid at the same temperature. So what is the temperature at the inlet number 1? 80 degrees Celsius. This one is HF at 80 degrees Celsius. What about the inlet number 2? The temperature was 20. So this one is HF at 20 degrees Celsius. What about the exit? 42 degrees Celsius. So this one is HF at 42 degrees Celsius. So let's find them from table A2. Here is HF. At 80 degrees Celsius, we're looking at 334.91. 334.91 kilojoule per kilogram. At 20, 83.96. 83.96 kilojoule per kilogram. At 42, oh, where is 42? Between these two numbers. So you can do linear interpolation between these two numbers to determine HF at 42. If you do, you get 175.92 kilojoule per kilogram. Now, the inlet number 1, at the inlet number 1, the mass flow rate is 0.5 kilogram per second. So this one is 0.5 kilogram per second. And we have one more governing equation. M dot number 1 plus M dot number 2 is going to be M dot number 3. In this case, M dot number 1 is what? 0.5 kilogram per second. And there's no information about heat loss from this mixing chamber, so you can neglect the rate of heat transfer from the control volume. Then how many unknowns do we have? M dot number 2, M dot number 3, M dot number 2, M dot number 3. How many equations do we have? 2. How many unknowns do we have? 2. Can you solve it? Yes. Then what do we need to determine? We need to determine the mass flow rate of the cold water stream. So that is M dot number 2. So from this, M dot number 2 is going to be 0.864 kilogram per second. So that's how you solve this problem. Anything difficult? And the 3, that is one of the unknowns. So there are 2 unknowns, this one. And you have 2 equations. So if you have 2 equations, 2 unknowns, can you solve it? Yeah, because here you can say M dot number 3 is M dot number 1 plus M dot number 2. So you can say this one is M dot number 1 plus M dot number 2. Then how many unknowns in this equation? 1. So you can solve it. So in mathematics, if we have 1 equation, 1 unknown, you can solve it. If you have 2 equations, 2 unknown, you can solve it. 3 equations, 3 unknowns, you can solve it, right? So you need the exact number of variables So number of equations and number of the variables should match each other to solve them. Any question? In chapter 4, what we did is pretty simple. We first study each thermodynamic device and look at the physics of the thermodynamic device. Based on that, solve mass balance and energy balance. So we come up with mass balance equation and energy balance equation, and by solving these two energy balance equations or mass balance equations, you can find any unknown. That's what we did. For nozzle diffuser, turbine compressor, throttling valve, now heat exchanger, and now mixing chamber, and the last steady state open thermodynamic device is going to be this one, heat exchanger. Heat exchanger. This is the last one. In other words, this is the hardest one. In other words, this has the highest possibility to be in your second exam, right? Heat exchanger is widely used in our real life. Do we have a heat exchanger here? Yes. 1, 2, 3, many. Name one. AC unit. It has a heat exchanger. Why? What is the working fluid of AC unit? Air? No, refrigerant. So refrigerant is flowing between the outside of the building and inside of the building, and they undergo phase change, trying to pump heat from inside to the outside. And do we want to breathe refrigerant? No, we don't. So we have a heat exchanger in the the air handler unit where refrigerant and air can exchange heat without mixing. That is a heat exchanger. What about outside? Do we like our refrigerant go to be released to the air? No, we don't want. So there is a heat exchanger outside where the refrigerant can lose heat to the air outside without being released to the air. What's going to happen if we release refrigerant outside? Have you heard about freon gas destroying the ozone layer, causing our skin cancers? That is one of the most famous refrigerant. Then, what else? We have a heat exchanger in this computer where air flows, where fan blows air, and this air, the passing through a heat exchanger to cool down the CPUs inside. What else? In your car, if you open your car, open your engine room, unless it's not unless. So if you open the engine room, what you see in front of your engine? A giant fan is blowing air to where? There's a number of things are there, right? That is heat exchanger. So there's a coolant flowing through inside and air is flowing outside. We don't want them to be mixed, but we want to, the exchange heat. So coolant losing heat to the air, but without mixing. That is heat exchanger. The heat exchanger is everywhere in our life. And this is the simplest way, the simplest schematic to show a heat exchanger. But if you design a heat exchanger in this way, you're not going to find a job. The reason is that, what do we want? We want to exchange heat where, the heat transfer occurs on the interface between two fluids. So if you want to maximize the rate of heat transfer, you need to maximize the surface area between two fluids. That's why if you look at the the fins in your the car engine, you see a number of the many the panels are aligned together, trying to increase the surface area. So if I to make a heat exchanger like that, you may want to add a number of fins like that, trying to increase the surface area so you can exchange heat more in a limited volume. Okay? Anyway, then, how can we analyze this heat exchanger? Analyzing a heat exchanger thermodynamically is slightly different from what we did in the past. Why is that? How many systems do we have? One? Just one fluid? No, we have two fluids. fluid A and fluid B. That means we can come up with energy balance equation only for fluid A, another energy balance equation only for fluid B, and the last energy balance equation for both of them. So for one heat exchanger, we can come up with 3 energy balance equations. So that's what we are going to study. In this slide textbook, it shows only one, but you can actually come up with 3 energy balance equations. That's what we are going to study. So here we have a heat exchanger. So we have one fluid flowing this way, entering this heat exchanger. So we have a control volume this much. That is control volume. Then we have a fluid entering this heat exchanger in this inlet. So I'm going to say inlet number 1. This fluid is going to exit the heat exchanger here. So that's exit number 2. There's another fluid entering this heat exchanger from the top. That is the inlet of the other fluid. Let's say number 3. And the exit of this fluid is going to be number 4. So we have 4 inlets and exit. Then let's say the fluid entering at number 1 is going to be fluid A. And the fluid entering at number 3 is going to be fluid B. Then there should be heat exchange. It means that there is a heat transfer within this control volume. What is the condition to have a heat exchanger? What is the condition to have a heat transfer? According to the second law of thermodynamics, to have a heat transfer, you need to have temperature difference. Right? If you grab this cup of coffee, you feel that it is hot because there's a heat transfer. Why there's a heat transfer? Because the coffee is at higher temperature than your hand. That's why there's a heat transfer. If there is a heat transfer, that means one is at higher temperature than the other. So let's assume that fluid B is at higher temperature than fluid A. Then what is the direction of heat transfer? This way. So there's a Q dot. This way. From fluid B to fluid A. So this is the physics of the heat exchanger. Now let's talk about the mathematics of the heat exchanger. There are 2 conservation principles that we know. One is mass balance, mass conservation. So let's apply mass conservation. For what? 2. One for A, the other for B. So let's apply mass balance for A. And mass balance equation for steady state open system is m dot that goes into a control volume should be the same as m dot that comes out of the control volume. So mass transfer entering a control volume should be the same as the sum of mass transfer leaving that control volume. So what is the mass flow rate goes into this control volume for fluid A? Number 1. M dot number 1, this is for A, should be the same as exit. M dot number 2. So they are the same. I'm going to say this is the mass flow rate of fluid A. What about fluid B? The inlet is number 3, the exit is number 4. So for fluid B, the inlet is number 3, the exit is number 4. So I'm going to say m dot of fluid B. So we came up with 2 mass balance equations. Now, energy balance equation. How can we determine the energy balance equation for this heat exchanger? Always start with the general energy balance equation. What is the general energy balance equation? Q dot in plus, so the sum of all energy transfers into this control volume There are three energy transfers. One is by heat, another is by work. The last one is by mass. So mass flow rate that goes into the control volume. This mass flow rate has three forms of energy. Specific enthalpy H, specific kinetic energy velocity square over 2 plus specific potential energy gravity times elevation Z to be Q dot out plus W dot out plus M dot that goes out of the system. It has specific enthalpy, kinetic energy, and potential energy. So now let's find the energy balance equation for fluid A first. So this time for fluid A. For this fluid A, is there heat transfer? Yes. Q dot coming from B to A. So that is incoming heat transfer for A. So this Q dot in is this Q dot. So we have Q dot. Is there any energy transfer by work? No. Q dot out? No. That Q is incoming, not outgoing. So we can neglect W, W, Q out. What is the inlet? Number one. M dot number one. And we need to consider enthalpy. What about kinetic energy, potential energy? We can neglect them. M dot number one, H1 is going to be, we can neglect kinetic energy change, potential energy change. What is the exit? Number 2 for fluid A. M dot number 2, H2. So that is the energy balance equation for fluid A. I'm going to say right here for fluid A, the energy balance equation is Q dot plus M dot number 1, H1 is M dot number 2, H2. But that's not it. According to this mass balance equation, M dot number 1 is the same as M dot number 2. So we can just say M dot of A. We can just say M dot of A. Then why don't we move this one to the right-hand side? The energy balance equation for fluid A is going to be Q dot is M dot of A, H2 minus H1. Now, let's talk about fluid B. For fluid B, so fluid B is losing heat to fluid A. So is there incoming heat transfer? No. There's outgoing heat transfer for this amount, Q dot. Is there energy transfer by work? No. Is there kinetic energy change, potential energy change? You can neglect them. Inlet is number 3. Exit is number 4. M dot number 3, H3. M dot number 4, H4. So that energy balance equation is going to be this one. M dot number 3, H3 is Q dot plus this one. M dot 4, H4. By the way, according to this mass balance equation, M dot 3 is the same as M dot 4. So we can just say M dot of B. Let's move this one to the left-hand side. We get M dot of B times H3 minus H4 is Q dot. The last one, we are going to assume that A, B together. So the entire control volume is our system. So do we have an incoming or outgoing heat transfers? Yes or no? Yes, really? What, this Q dot? This Q dot, is this Incoming or outgoing? Is it incoming? Incoming? So this green is our system, okay? So green is our control volume this time. We are considering both of them is our system. So is this Q dot incoming or outgoing? None of them. That's what happens inside. So when we talk about energy balance, what is the first example I gave you on day one? Eating 3 hamburgers in the morning, pooping 2 hamburgers in the afternoon. How many hamburgers in your body? 1. So do we consider hamburgers that comes from stomach, one stomach to the other? I don't care. It's not eating or pooping. So whatever happens inside the control volume, do we consider them or not? No. So there's no incoming or outgoing heat transfer. That's what happens inside. Then what if I want to determine this Q dot? You can use either A or B, not both. Energy transfer by work, you can neglect them. Kinetic energy change, potential energy change, no. So only incoming rate of enthalpy, outgoing rate of enthalpy. So what is incoming rate of enthalpy for the entire heat exchanger? Number 1, number 3. Outgoing, number 2, number 4. So incoming, number 1 and number 3. Outgoing, number 2 and number 4. M dot number 2 H2 plus M dot number 4 H4. So the energy balance equation, A plus B is going to be M dot number 1 H1 plus M dot number 3 H3 is M dot number 2 H2 plus M dot number 4 H4. How many unknowns? 1, 2, 3, 4, 5, 6, 7, 8. Too many, right? So what we can do? We know M dot number 1 is the same as M dot number 2. So let's say M dot of A, M dot of A, M dot of A. We know M dot number 3 is the same as M dot number 4. So let's call it M dot of B. M dot of B, M dot of B. Now, can you move this one to the right, this one to the left? Then the energy balance equation is M dot of B, H3 minus H4 is M dot of A, H2 minus H1. Then how many unknowns? 1, 2, 3, 4, 5, 6. So 1, 2, 3 energy balance equations. That's all. That's everything about heat transfer. Heat exchange. Any question? So we studied the physics of a heat exchanger, the mathematics of the heat exchanger. Looks much more fun than the other thermodynamic devices. So if I design a problem for your second exam, pretty high chance I put this one there, right? So what do we do now? Solving a problem. Now we are going to solve a problem. Now we are going to solve a problem. We are problem solver. Okay. We have a steam entering the condenser of a steam power plant. What steam power plant? If you want to study this one, you can solve it, assuming that this condenser is just heat exchanger. But you may want to know how this steam power plant works. What is a steam power plant? We use steam as a working gas, and then we run a turbine to produce electricity. That is a steam power plant. That's how we produce electricity in this classroom. Many people are saying that, oh, there's a solar panel, there's a, the wind, turbine, etc., etc. However, the majority of electricity is produced by steam power plant. And how do we run our steam power plant? We first need to make steam. By how? By using steam generator. It's like heat steam that passing through this steam generator so that we can produce steam. So while passing this steam generator, so water is passing this steam generator, it evaporates, it becomes steam, high pressure, high temperature steam. Then what do we do? To produce electricity, we are going to use a turbine. So this high pressure, high temperature steam enters this turbine. So producing this shaft power, W dot by this turbine. This is turbine. So we have high pressure, high temperature steam expands in the turbine, and there are many turbine blades. While it is expanding, it moves to the right. It pushes turbine blades. That's how we produce this shaft power. And at the end of this turbine, what do we have? Here, useful high temperature, high pressure steam? Not anymore. Now, the steam has lost all the energies, not all of them, most of them. So we have a low pressure, low temperature steam exits this turbine. Low pressure, low temperature steam exits the turbine. Now, how useful this low temperature, low pressure thermal energy is not that useful. So if it is not useful, what do you want to do? You want to get rid of it, right? By how? By using coolant. So we have a condenser. We have a condenser where we pump water from nearby lake or river or something. Then you can cool this steam. So that's where coolant runs through. So we can remove, we can, reject any waste, the heat from the steam. Now we have a, now we are ready to put this back to this steam generator so we can produce good quality steam. But we don't have power anymore, so let's use a pump to pump this, the steam back to the steam generator. That's where we accept some power, pumping power is needed to pump this water back to the steam generator, where heat is provided to produce high temperature, high pressure steam that produces mechanical power. Now, what do we need? We just need a generator to produce electricity. So that is generator. So here we provide heat, Q dot in. Here we reject heat by heating this coolant. This is called the famous Rankine cycle. Rankine cycle. This is how we produce electricity in the world. Then, what is the condenser here? This is the condenser. This is what you see here. This is the condenser. Low pressure, low temperature steam. Low pressure, low temperature steam enters, and this coolant is cooling, removing any waste heat. So this steam can go back to this steam generator to become more useful steam at high temperature, high pressure. So that's what we analyze in this problem. Then, so to remove any waste heat, we need a large quantity of cooling water. That's why many giant power plants are installed, built near a large lake, like Michigan Lake, Lake of Michigan, or ocean, or lake. So that's what happens. Okay. Then let's analyze this condenser thermodynamically. How can we do that? We can use the same approach here, making this a schematic and write down the energy balance equation and solve it. So we have this heat exchanger, looks like this. And we have a coolant entering here. The inlet of the coolant is number 1. The exit of the coolant is number 2. The inlet of the steam is number 3. The exit of the steam is number 4. Then what do we want to determine? Determine the mass flow rate of the cooling water. So we want to determine m dot number 1. Okay, from the previous example, we came up with 3 energy balance equations. We can use the first 2 if we are interested in this Q dot. However, we don't want to determine Q dot. We want to determine M dot. Then we can use the third one. So let's use this one. So the energy balance equation looks like this. And I'm going to say steam, the mass flow rate of the steam is m dot number 3 is the same as the flow rate at the exit. And I'm going to say this is m dot of S, steam. What about the mass flow rate for this cooling water? M dot number 1 is the same as m dot number 2. I'm going to say this is m dot of cooling water, C. Then this energy balance equation is here. We can say m dot of steam times H3 minus H4 is m dot of cooling water, H2 minus H1. This is the energy balance equation we are going to solve. Okay. Now we need to check what do we know and what we do not know. So first one, m dot of S, the mass flow rate of the steam is given 20,000 kilogram per hour. That is the mass flow rate of the steam. This one is 20,000 kilogram per hour. Do you like hour? You don't. You prefer second. So 1 hour is 3,600 seconds. What about H3? Can we determine H3? 3 is the inlet of the steam. So let's see what do we know at the inlet of the steam? Steam enters, so there's an inlet condition, at 20 kilopascal, and quality is 95%. So we have a quality between 0 and 1. So it is a saturated mixture. If we have a saturated mixture, how do you determine this enthalpy? You can use linear interpolation. H3 is HF plus quality X3 times Hg minus HF, because we know it is saturated mixture. Then how do we determine HF Hg? From the pressure table. What is the pressure at the inlet of the steam? 20 kilopascal. So HF is at 20 kilopascal, Hg is at 20 kilopascal. So at 20 kilopascal, here is HF, here is Hg at 20 kilopascal. So I'm going to write these numbers here in this equation. This is HF 251.4. What is the quality X? 95%. So 0.95 Hg, this number 2609.7. HF, again this one, 251.4. So we have everything. Can you determine H3? Yes, it is 2491.8. Now, H4, so the specific enthalpy at the exit of this steam. What is the exit condition? If the steam is to leave the condenser as saturated liquid at 20 degrees Celsius, so we already know the phase change process. If it is saturated liquid, how do we determine H? That H is going to be H of saturated liquid. At what condition? At 20 kilopascal. HF at 20 kilopascal. So what is HF at 20 kilopascal? At 20 kilopascal, this is HF, 251.4. So we know everything on the left-hand side of this equation. What do we want to determine? We want to determine the mass flow rate of the cooling water. So this is our unknown. Then if you know H2 minus H1, we can determine m dot of the cooling water. So how do we determine H2 minus H1? It depends on the on our system. So what is our system? It is the cooling water from the nearby river. So what is the phase change process of this cooling water? How? In other words, the question should be, is there any phase change of this river water? Now, it could be very interesting if there's a phase change. So then we can get pre-cooked fish from Chippewa River. So there's no phase change for this river water. So can we assume that this river water is going to be pure liquid? Yes, we can. And if it is pure liquid, how do we determine H2 minus H1? How do we determine H2 minus H1 if it is pure liquid? If we have a pure system, without phase change, H2 minus H1 is CpT2 minus T1. U2 minus U1 is CvT2 minus T1. You remember this from chapter 3? Yes, specific heat equations. So here is H2 minus H1. We can use a CP T2 minus T1. So this whole thing is going to be CP T2 minus T1. What is T2 minus T1? The temperature rise of the river water is only 10 degrees Celsius. The temperature rise of the river water is only 10 degrees Celsius. So this whole thing is going to be just 10. What is the specific heat? Specific heat can be found from table A19, properties of selected liquids. For water, specific heat values are given here with temperature. So what is the typical temperature of river water? Around room temperature, reasonable gas. So let's assume 300 Kelvin. Specific heat is going to be 4.179. 4.179 kilojoule per kilogram degree C. Now we have everything. Can you determine m dot of C? Yes, 297.8 kilogram per second. That's how you solve this problem. Oops. Any question? So when you study this problem, after this class, think about this way. If I see this problem in my second exam, can we solve it? So you need to practice as many times as you can to make sure that you can solve it in the exam. So this completes steady state open system. However, this is not the only open system. This is just steady state open system. There is unsteady open system. So let's talk about energy balance equation for unsteady open systems. So let's talk about unsteady open system. So how can we come up with its energy balance equation? It's not that hard. We can do that together here. So we need to start with the first equation that we studied from day one, the conservation of energy principle. What is the conservation of energy principle? Energy transfer into our system minus energy transfer out of our system should be the same as the change of energy of a system. How do we determine the change of energy of a system? We studied it in chapter 3, U2 minus U1 plus moving boundary work. If it is constant volume, U2 minus U1. If it is constant volume process. If it is constant pressure process, H2 minus H1. So that's how we determine the right-hand side. What about the left-hand side? Energy transfer into a controlled volume. So what kind of energy transfer we studied? There are energy transfer by heat Q. There are energy transfer by heat Q, and energy transfer by work W, and energy transfer by mass entering the control volume. M that goes in to a system. And this mass has three forms of energy: enthalpy, kinetic energy, potential energy. So these are energy transfer into a control volume. What about energy transfer out of the control volume? The same thing. Minus Q out plus W out plus mass at the exit. This one has enthalpy, kinetic energy, and potential energy. Is this U2 minus U1 plus moving boundary work, or U2 minus U1, or H2 minus H1, depending on whether it is constant volume or constant pressure. So that is the energy balance equation. What about mass balance equation? Mass goes into a system minus mass leaves the system should be the same as the change of the mass. The final mass M2 minus the initial mass M1. So that's the mass balance equation. So these two are the governing equations for unsteady open system. One thing, the biggest difference between here and steady state open system is there's no dot, because these dots are convenient for steady state system. Here is an unsteady system, so we don't have it. Then let's solve a problem together. This is the last problem. On insulated vertical piston cylinder device is set insulated, so there is no heat transfer. Nice. Let's remove them. And there is initially contains 10 kilograms of water, so M1 is 10 kilograms. M1 is 10 kilograms, and 6 kilogram is vapor phase. So 4 kilogram liquid, 6 kilograms vapor, so it's a mixture. What is the quality X? 0.6. So quality X at the initial state is 0.6. What is the pressure? 200. T1 is 200 kilopascal. So that is the inlet condition. Oh wait, it says it maintains a constant pressure. So it's a constant pressure process. The right-hand side should be H2 minus H1. And now steam at 0.4, it's a typo, it's just 4, not 0.4. 4 megapascal and 360 degrees Celsius is allowed to enter the cylinder from a supply line. So that is the inlet. 4 megapascal, 360 degrees Celsius. If you make a property diagram, you will know this is two-point vapor. Since we did many times, I won't do that. So at the inlet, T in is 4 megapascal, and T in is 360 degrees Celsius. Until all the liquid in the cylinder has vaporized. So what is the phase change process at the end? Saturated vapor. So at the end, P2 is still 200 kilopascal because it's a constant pressure process, and it is phase change process number 4. So we have everything that we need to evaluate H initially, finally, and at the inlet. There's no information about energy transfer by work, so you can neglect them. You can neglect kinetic energy change and potential energy change, There's only one inlet, there's no exit, so you can neglect this one too. So what is the energy balance equation? The energy balance equation is M in H in is H2 minus H1. Energy balance equation is M in times H in is H2 minus H1. How do we determine H2? M2 H2. How do we determine H1? M1 H1. So this is the energy balance equation. Mass balance equation, there's no M out, so it is M in is M2 minus M1. So this is mass balance. Then let's see, what do we know? We know the initial mass, 10 kilograms is initial mass, 10 kilograms. So this one is 10 kilograms, this one is 10 kilograms. What we want to determine? We want to determine the mass of the steam that has entered. So the unknown is going to be mass that has entered. So it means we need to determine H in and H2, H1, then you can determine M in. So can we determine H in? Yes, it is 4 megapascal, 360 degrees Celsius. That is superheat vapor. So you can go to superheat vapor table, which is table A4. 4 megapascal, 360, H is this number. 3,117.2. What about H2? 200 kilopascal saturated vapor. So it is Hg at 200. Hg at 200 kilopascal. At 200 kilopascal, Hg 2706.7. H1. We know H1 is saturated mixture. If we have saturated mixture, how do you determine its H? By using linear interpolation equation. How do we determine HF and Hg at 200 kilopascal? Where are they? This one HF, this one Hg. 504.7. What is the quality X? 0.6. Hg 2706.7. HF 504.7. What is H1? 1825.8 kilojoule per kilogram. So this one goes here, 1825.8. So we have everything. Can you determine M in? Yes, we have 1, 2 unknowns, 2 equations. You can determine M in. If you do, M in is 21.46 kilograms. What is the final temperature? Finally, it is saturated vapor. So what is the temperature of saturated vapor? Saturation temperature at 200. Saturation temperature at 200. 120.2 is the final temperature. So this is the final temperature. T2 is going to be T sat at 200 kilopascal, which is 120.2 degrees Celsius. So that's how you solve this problem. Any question? Saturation temperature at 200 kilopascal because it is saturated vapor. So this completes chapter 4. We have a new homework assignment due by a week from today. Huh? I don't remember. But it should be less number than homework number 3. Yeah. All right, that's all. Thank you.